So, okay, and this will be, you could define a probabilistic measure on this propositional structure and obtain a model of a non-classical probabilistic calculus. And you can complain because you say, well, the Firefly is a classical system. I could not play this game, your game, and just look at the thing from above and from all sides and just determine where the Firefly is and get a classical probabilistic model out of it. And that is true. But the idea is that in quantum mechanics, this will be for real. We will have systems that can be prepared in states for which there are complementary experiments that cannot be performed at the same time by any means because they are incompatible. So now it is not a game. Nature doesn't allow you to do that. And again, you will obtain this structure. You will obtain a Boolean algebra for one experiment, and if you change the setup and performs a complementary experiment, you will obtain a Boolean algebra, and the whole thing, the whole propositional structure will not be Boolean. So the probabilistic measures that you define on this structure will not be Kolmogorovian. Why? Because now the algebra will not be Boolean anymore, and the properties of the probabilities or measures that you define on this system will not be the same as those of classical system. They will only be the same when you restrict to a Boolean subalgebra. If you just move here and never mix the results from here and there, you can stay on classical or Kolmogorovian probability. But when you mix propositions from here and from here, you break the rules of Kolmogorovian probability. Why is this so? Let me just tell in a nutshell what happens with quantum mechanics. If elementary particles were just small balls like this, and we throw the balls like one by one through a two-slit experiment, then what you will, if they were just balls, what you would expect as an outcome is that some balls go from the enter on the left and some on the right, and you will obtain something like this, like the balls that pass the screens. But you don't get that. You don't really get that. You get something more like waves. Like, for example, when you make an interference experiment with light, like a fringe with a collection of fringes, bright and dark fringes, and you get an interference pattern. And then something very important happens. Under certain circumstances, you can prepare the quantum systems in such a way that you hit in this is a screen when you collect where the particle is detected, and they hit the screen one by one. But when you make the statistics and throw dozens of them and then collect the statistical data, you will find that they form a pattern. And this pattern has the shape of a wave, as if it were an interference pattern. So this experiment here will be a wave-like experiment. And this experiment doesn't allow you to conclude which slit the particle passed. So if you do this experiment, you cannot decide what was the path taken by the particle. But the strange things, or the surprising thing, is that if now I try to perform an experiment in order to determine what happened here, so I will put a detector symbolized here by an eye that looks which slit did the particle go, then the interference pattern will be destroyed. So the phenomena changes according to the experimental setup devised. So you have this probability distribution here, because of course there are fluctuations. You cannot predict which slit will, but this probability is compatible with particle trajectories. And this one is compatible with wave-like trajectories. So there are two complementary experiments that cannot be performed at the same time that give you two different probabilistic distributions. So the quantum state has the information as a mathematical object. The quantum state gathers the information for both experiments. And the quantum state, as I explain you very soon, can be considered as a measure, as in measure theory, as I showed you in Kolmogorov actions, but this measure will no longer be a measure over a Boolean algebra, but on a very different mathematical object. Not so very different, because Boolean algebras are orthomodular lattices, and also the lattices that appear in quantum mechanics are of the same kind, but have algebraic differences, and this will lead also to geometrical differences, as we will see. So I will skip the actions of quantum mechanics because I don't want to go into calculations. Of course, I leave it here because if some debate appears afterwards, we can come back to this and look at the details. But I will not speak about the quantum formalism. But the thing is, from a geometrical point of view, don't worry if you don't know enough mathematics. A quantum state can be described as a trace class operator acting on a Hilbert space, trace class operator of trace 1. So it will be positive, and the positive operators will form a cone. It will be trace 1, and trace 1 operators form a hyperplane, so you have to intersect the cone with the hyperplane. And then you will get a convex set here. Again, the same as in classical probability, but this guy here is not a triangle or an n-simplex anymore. It will be a very different mathematical object and much more complicated. For the case of qubits, which is the most simplest, which are the most simplest quantum system, the shape of the set of quantum states is a sphere. Remember that the ball, that the coin, which was the simplest classical probabilistic system, the coin was a line segment. Now, the simplest quantum system will have the geometry of a sphere. So, in classical systems, you have subset of a given set. And this was a Boolean algebra. You can form the disjunction, which is set union, the conjunction, which is set intersection. You have the partial order relation, which is set inclusion, and the negation, which is set complement. Now it is all the same, but instead of sets, you have subspaces of a linear space. So now events in quantum mechanics will be represented by subspaces of a separable Hilbert space, and this will have the structure of an orthomodular lattice. You can have something like conjunctions and disjunctions, and a negation, but these connectives will no longer have the same interpretation as they have in classical logic. So this is why, one of the reasons why this was called quantum logic by Virchow and von Neumann. Of course, if there are logicians here, logicians don't like to call quantum logic a logic. So the agreement is that it is an algebraic structure, but a very important one because it allows to define a set of actions which are very similar to those of Kolmogorov that allow to recover quantum states as in the shape of a measure theory, as we will see now. So just to give an idea, a proposition like this, like S subspace, represents something like the value of observable H lies in the interval AB. That could be, for example, the value of the energy lies between 1 joules and 3 joules. Not joules, like 1 mega electron volt and 2 mega electron volts. So that's the kind of testable propositions. Like the ball is on my left hand, the ball is on my right hand. That for this thing here will be a Boolean algebra because this is a classical object. But for a quantum system, it will not be a Boolean algebra. But the idea of proposition, of empirically testable proposition, is pretty much the same. The problem is that the algebraic structure that we use to represent those empirically testable propositions are not isomorphic to those of classical mechanics. So, for example, this law of distributivity, which holds some Boolean algebras, is no longer valid, and the same for example, you know this from elementary school. If you look at Venn diagrams and sets and compute areas, you will see that this is valid. But this will not be valid for quantum probabilities. Whenever A and B come from incompatible measurements. So each time that you mix the statistic from one context with the statistic of a complementary context or experiment, you will end up in a violation of Kolmogorov's axioms. So, a quantum state can be represented by a function that goes from the algebra of testable propositions of quantum systems, which will be projection operators associated to a Hilbert space, to the interval 0, 1 that satisfy that the probability of the null proposition is 0, the probability of the negation is 1 minus the probability, and so on. It's very similar to those of Kolmogorov. The difference lies in the fact that this guy here is not a Boolean algebra anymore. So with these axioms, Gleason's theorem allows us to say that each measure of this form will be represented by a quantum state represented by a density operator and vice versa. So the shape is very similar, but the algebraic structure is not. And the geometry of the object defined by these actions will be very different too. It will be indeed much more complicated. So remember, this was the simplest Boolean algebra, the Boolean algebra of two elements. Now, the simplest quantum system will have something common. But let me explain how is the phenomenology of this. The simplest quantum system is a spin 1/2 particle. So you have an array, or you can throw them one by one, spin 1/2 particles, and make them pass through an inhomogeneous magnetic field. And then if you prepare the system in a given state and make an orientation of the magnetic field in a chosen direction, you may have two possible results, up or down. And that will be just like a coin, because the quantum state will give you the probability of going up and the probability of going down. But now, unlike the coin, you can do a measurement in a different direction, which is incompatible, because you cannot orient the magnet in two different directions at the same time. So you have to make a complementary experiment, like in the firefly. But this is ontological, because you cannot do that. So when you do that, you obtain a new coin, up and down, with new probabilities, and so on, infinitely many directions of space. So look at this. The Boolean algebra only has one experiment, one empirical context. But in the quantum case, so you have the Boolean algebra structure here, 0, 1, x, y. So this one is the negation of this one, right? Because if this one happens, this one does not happen, and vice versa. And the quantum case will be like this. In one direction, you have one proposition and its negation. And this is a Boolean algebra. But besides this one, you will have this one. And so on, infinitely many Boolean algebras pasted together. And the quantum state defines a measure, in the sense of measure theory, over this algebraic structure. And you can show that this is equivalent to the density operators formalism, or for pure states, normalized vectors on a Hilbert space. What happens with the Q-treat? Well, it's pretty much the same. Now you will have each experimental context will be isomorphic to a Boolean algebra of 3 elements. But now this guy's here, I put the old Boolean algebra just to compare. It's isomorphic, but these ones are sets and these ones are projection operators. The difference between the quantum and the classical cases is that the quantum case cannot be reduced to one measurement context. You need infinitely many measurement contexts in order to define the quantum state.